video's in two parts because we had a fire drill. Okay, so we're updating our formula sheets with the RAP formula. It's very, very easy to use, and I will show you on the next page how to use it. And it starts with our calculators and putting table values in our calculator using STAT, if you remember. So if you're waiting, feel free to go ahead and pick up your calculator and clear the RAM. What? Where? I was out there. I walked out with you. I said, it's a beautiful day. And then I was talking to another teacher. I don't know. I was there. Okay. I did not. All right. If anybody didn't get the rest of the formula, let me know when I'm done. I'll bring it over to you. All right. So listen. Here we go. Here we go. The weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Okay. So here's a table of values with the weight in kilograms of babies T months after birth. Okay, so inputs, outputs, X's, Y's, independent, dependent, whatever you want to call them. What we're going to do is use the regression capability on our calculator to find a linear model in slope-intercept form. Ignore that. So you guys know where to go. We've done it a bunch of times, even recently. We go to Stat, Enter, and then you're going to put your table of values in. So what you're given here in this table of values is real-world data. This is actual weights, like somebody recorded the weights of some baby. So this is actual real-world data, okay? We're going to put it in our calculator and ask our calculator to make it into a linear equation. And when we do that, it's going to take this data and squeeze it somehow into slope-intercept form. It's going to find like an average slope, because if you take a second and just look at what your first differences are, you're adding 1, you're adding 0.9, you're adding 0.7. It's not exact because it's real-world data. What your calculator will do is scrunch it and crunch it and crumble it and move it into a slope-intercept form that matches that data as closely as possible, okay? So go to Stat, over to Calc. Linear regression is number 4. We always want to save it. What's that buttons? What are those buttons? Alpha trace. Enter, enter, enter. And there's our slope-intercept form. And remember, when we use this symbol here, it's called Y hat. It's okay if you don't, but you're going to see it, so I just want you to know that that means that this is a model. This was we got this from our calculator. So this is the model used to make predictions. We can type in any month and see what the weight would be. You could type in a weight and say, when approximately would that happen? When will the baby be 10 pounds? Or what weight will the baby be at 10 months? It just depends on what you want to find. So this is actual data. This is the model. And since we saved it, you know it's up in Y equals. You could hit graph and see the line. But what I want you to look at is the table. So if you look, I want you guys to understand, because I've had students ask this before, so I want to make a point. First of all, what does 0 mean? Like how would you describe, what does 0 mean? How is times 0 weight is 3.2? What does that mean? Yeah, the initial value. Remember when x is 0, a sub 0, or whatever? That's when the baby's born, time has not started yet. The baby's born weighs 3.2 kilograms after 1 month and so on. Now, my table of values here is a little bit different, right? They shouldn't match. This is what the calculator came up with that matches. It's the model it came up with. So if you plug in 0, you'll get 3.4. If you plug in 1, you'll get 4.14, and so on, okay? That's why they're different. This is model. This is actual. This is another word for model is predicted, okay? So just so you know, I'll move my paper. And model predicted. All right, stay with me. Use the model found in part A to predict the weight of a baby at 2.5. So that's my X value, right? So you could do two things. You could plug 2.5 in right here and just do the math on your calculator, or you could go to your table. It's probably quicker to just plug in as a slope-intercept form. It's nice and easy. But you could use your table and do your change in table to see where it says change in table, it's counting by ones. If I want it to count by 0.5s, or I could have just told it to start at 2.5, one or the other, both, it's fine too. And that would tell me at 2.5 months, at 2.5 months, the baby would weigh 5.34 kilograms. So whether you use the table or actually did the mathematically yourself, you should get the same answer. Yes? Okay, so you know how to go to the table, Jeremy? Okay, and then, so I went to table set. Okay, so that's above window, like set the table, set up the table. Okay, and table start will always say 0, and change in table will always be 1. You could just change one or the other, and you didn't really have to do both. And then that's how you could find numbers that were different. Okay, and then go back to your table. Nikki, do you see that? Does that make sense to you? Okay. If I went too fast over that and you still had a question, please, in a few minutes, I'll come over to anybody that needs help. Okay. You know I'll always help you. Just don't forget to ask me. Okay. All right. So we could make a prediction using our model, right? We made a prediction using the model. Now, here's where I finally tell you about what residuals are. The actual weight of this baby, 2.5 months after birth, was 5.5 kilograms. That's actual real-world data, right? What is the residual? So residual is the A minus P. Remember RAP. And I'll tell you what a residual is used for in a minute. A residual, let's just find that now. Mathematicians, you want us to plug into a formula, we can do it like bosses, right? Actual weight would be 5.5. And then predicted would be the 5.34, right? This is the prediction. That, whatever over there, is the actual, right? Understand the words, what actually happened, and what did our model predict for us, okay? And we literally just subtract the two numbers, and you should get an R value of 16 kilograms. That's the difference between what happened in the real world and what our model predicted. Sometimes this number is a positive number, and sometimes it could be a negative number, depending on which one's bigger, okay? So the question is, did our model, so this is where common sense kind of has to come in. Just listen. Does our model underestimate or overestimate the actual weight of the baby? Under or over? Under, right? Because this is the actual, this is the model or predicted. Model, predicted mean the same thing. So our model underestimated. I used to teach this and say, okay guys, if you get a positive number, it's underestimated. If it's a negative number, it's overestimated. I don't want you to memorize something like that. If you understand the question, you'll really understand it when the time comes. Because, slope, do you guys have to make note cards anymore that this is a positive slope and this is a negative slope, or a lot of the easy things? 9 times 4 is 36. No, you use it all the time, so you know it. This is something you'll use 3 times in your whole life, probably. So instead of trying to memorize things, just understand what it's asking. This model was less than what actually happened. It underestimated what actually happened in the real world. Okay? Now, what the people in the classroom a few doors down do in statistics, so AP Statistics taught by Ms. Bunday, they take this information and they go really, really deep with it. Okay? We don't do that in here, but we're going to just touch on it. So what the statisticians do is they take this residual and a whole bunch more, because we just found the residual of one weight, 2.5 months. But we could find the residuals for all of these, all of the 1.5, 3.5, all the way up to a year, whatever the criteria is for whatever the problem is that they're studying or something. So what a statistician does is finds a whole bunch of residuals, a whole bunch of these, and puts them on a graph that you're going to see on the next page. It is called a residual plot. So let me just show you what it looks like. I don't know if you have to flip a page or whatever, but that's a residual plot, okay? Taking all of those residuals. Now, this is not the graph of this. Remember, that's a line, okay? It's a graph of all the different residuals. We just found one. That's a whole bunch of them. And they use that picture, that residual plot, to answer a certain question, okay? We don't have to find a bunch of residuals. We might have to find one here and there and say over or underestimate. But one more thing that we would have to do is look at a residual plot and answer a question. Here's the question, very easy. If that residual plot has no pattern, that means the model was good, okay? Meaning, and we didn't do this, if I took a whole bunch of the residuals from this word problem that we just did and I made one of those and I saw no pattern, that means this was a really good model to match this data. If you see a very distinct pattern, you'd say, that was not good for that picture, okay? So let me show you what I mean. Look at example 3. An exponential regression was used. So they did a y-hat for a times b to the x. Okay? They made a model for exponential. And then they made a residual plot, and that's that. Okay? So they had a y-hat of a times b to the x, did a whole bunch of these, and graphed them, and that's what it looks like. So you can see it's a typical x and y axis, but really it's the y axis we're looking at. Right? So these are just 0, and then you have numbers that are greater than 0 or less than 0, and they're just plotted. But again, we don't have to do that. So do you see a pattern here? No. There is, and I'll show you what a pattern looks like in a minute, and you'll know the difference if you were confused. There is no pattern to this residual plot. That's a good thing. That means the exponential regression was a good model. So A and B say not appropriate, so we know it can't be those. An exponential model is appropriate because the residuals show no pattern. That's what you're looking for. It goes against what you think it should, okay? Let me do one more of those to really help you understand it. Because it's just really knowing, is there a pattern or not? That's it. And there's a multiple choice question on your test like this, okay? A group of AP Pre-Calc students used a set of data to create linear, quadratic, and exponential regression. So they did exactly what we did here, but instead of just finding linear, they did a linear y-hat, and a quadratic y-hat, and exponential. They did all 3. Then they found all of the residuals. Remember, we just found 1 from 1. And then they plotted all of those, okay? So what we have here is their linear residual, quadratic residual, exponential residual. Okay, these are not the graph of the line, the quadratic, and the exponential. It's the plus and minus numbers that we found using the RAP formula. Okay, so what they're asking is which model would be best, linear, quadratic, or exponential? So what do we think here? Does this first one have a pattern? Yes. This has a pattern. That's bad. We would not use linear, okay? This one also has a pattern. You can kind of predict at least roughly where another point would go, right? Roughly. These are considered patterns. We don't want a pattern. We want random. Some points above and below, just kind of like you dropped the points and they just kind of landed on there. There is no pattern here, which is what we want, okay? So not linear, not quadratic. Yes, we would use the exponential model. Why? No pattern to the residual. Want. Okay? So really, no pattern is what you want. Almost there. Mr. Passwater hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle radius r and feet. So is what he's doing, like, let's pretend that he's actually going to do some math to figure out how much paint he needs. Would that be linear, quadratic, or exponential? And when I first read this question years ago, I was like, what? And it's actually super simple if you think about it. Do you guys remember the formula for the area of a circle by chance? It's okay if you don't. It's pi r squared. That's how you find the area. So you would need to know the area of the circle to know how much paint to buy, right? Does that look linear, quadratic, or exponential to you? Quadratic, because it's got something squared. That's it. What would an exponential look like? It would have a percent in it. Like anytime you had like a percent, you knew it was geometric or exponential. Hint, hint, homework. You'll see that in the homework. Okay. Last thing. Should Mr. Passwater overestimate or underestimate? Does he hope that his model that he comes up with over or underestimates the amount of paint he's going to buy? Over, and why? So he doesn't. What? Why do we want to have more paint than less? So he doesn't run out. Okay. Kind of a dumb question, but like if you were asked to like put some thought into it, right? And the very last question I think in your homework does do that. Okay. The top of your homework says 1 through 11, but there's only 10 problems, so it's really only 1 through 10 on the next page. And because we had a fire drill, let me help you just get through the first page really quickly. Yep. Okay, guys. So table of values. You're going to say, is it linear, quadratic, or exponential? So remember, you have to look at your output values. And you can tell that this is a B value because 10 over 5 and 20 over 10 and so on equals 2. We're multiplying by 2. That makes it exponential. Okay? Kind of a review. But part 2 on these questions is really, this is the script, basically, that you have to be able to spit out on an FRQ. It's on one of your FRQs on the AP exam. That's why I'm making a big deal about it all first semester. It'll come up second semester, too. But remember, you have to say something about the inputs and the outputs. And the first sentence is always the same. Over equal length input value intervals. X values have to be equally spread apart. And then for exponential, output values are proportional. Or he said output values change proportionally. But you got to use that word proportional for exponential. 1 and 3 are both exponential. I'll tell you that. Okay. Look at number 2. First differences, second differences. Remember I started talking about that in the notes and I said I'd come back to it. See how you're subtracting 5. You're subtracting 7, 5, 3. You can steal the answers. If those were the same, it would be linear, right? If it was -7, -7, -7, it would be a linear equation. But it's not. So we go to the second differences, and we find, oh, now they're the same. That means it's quadratic. And I'm going to actually write my own. I don't like the way they wrote this. Over equal length input values. We always start with that. Input value, let's say intervals. The change in the rate of change is constant. Guys, first differences are rates of change. Those weren't constant. It's the change in the rates of change. Okay? The change in the rate of change is constant. That's the best sentence to write. And we will be memorizing these different statements right before we take the AP exam to make sure everyone gets that question right. It's like 2 points out of 6 on a question that if you have to say the words correctly. And there's 3 different little scripts. Okay? So, and then this one is proportional. Okay? I put the key on Canvas with a mistake on it. Number 6. If you're on Canvas, just know number 6. Number 6 should be D. D as in dog. Number 6 is D, not B, like the key says. I did write it on Canvas, but I'm guessing people wouldn't read it. Right? So I'm just going to put the next couple pages up for you guys because I definitely want you to do number 5 while you're sitting here because it's that calculator stuff. If you need me to bring you my formula sheet, I will. If you need me to show you something on the calculator, I will. Anything you need, I will help you with. That's the best I can do right now. Okay.